Welcome to the Explainer. Today, we're going to take a pretty wild journey, starting all the way up at the massive scale of semiconductor factory floors and zooming right down to the absolute microscopic level of chip architecture. We are looking at a complete paradigm shift in the industry right now, the massive transition from traditional silicon wafers to next-generation glass substrates in AI chips. It's a total revolution in both the materials we use and the geometry we design with, and it's all being driven by the absolutely intense demands of modern artificial intelligence.
To really get why this shift is happening right now, we have to start with this central sort of tech mystery. AI processors and high bandwidth memory are, they're getting exponentially larger, and they are running hotter than ever before. You just can't keep squeezing these massive, blazing hot AI brains into the same old packaging we've used for years. The traditional limits are literally breaking down. So how on earth is the industry solving it? Well, they're doing it by completely changing both the physical shape and the foundational materials of chip packaging itself.
Okay, let's kick things off with Part 1, TSMC's Square Glass Revolution. To grasp this shift at the macro level, like the actual factory floor level, think about a pizza box for a second. For years, the industry has relied on standard 300mm round silicon wafers for advanced packaging, like TSMC's CoWoS. But here's the rub. AI chips are large rectangles. Trying to cut massive square chips out of a round wafer leaves a ton of wasted edge space. It's super inefficient. Under 70% of the raw material is actually being utilized. Switching to square glass panels is essentially like finally baking a massive square pizza to perfectly fit that square box. By doing this, you virtually eliminate all that wasted edge space, pushing your raw material utilization well over 90%.
And to put that into perspective, the jump in area efficiency here is absolutely massive. According to industry analysis, if you utilize a large 600 by 600 millimeter square panel, your area efficiency skyrockets from a measly 45% on a traditional round wafer to a really impressive 81%. When we're talking about manufacturing ultra-high-end AI packages, getting that kind of geometrical advantage is just huge.
So by fixing that geometry problem and drastically cutting down on all that wasted space, TSMC is aiming for a unit cost reduction of up to 30%. 30%! That is a total game changer for manufacturing these massive AI processors at scale. But actually, changing the shape is really only half the battle. They also have to completely change the material to handle the insane heat these things generate.
And that is exactly where glass comes in. As a core packaging material, glass is being chosen over traditional organic plastics because it has a highly stable coefficient of thermal expansion, or CTE. When an AI chip processes a ton of data, it gets incredibly hot. Organic materials, they tend to warp and twist under that kind of extreme thermal stress. Glass, on the other hand, stays rigid and incredibly stable. It totally prevents that severe warping and acts as this pristine superhighway for electrical signals, ensuring pure signal integrity for the thousands of high-density I/O connections you need between an AI GPU and its high-bandwidth memory.
Which brings us to the next hurdle, Part 2, the through-glass via problem.
Here's the microscopic headache with glass. Yes, it's super rigid, but it's also incredibly fragile. To connect the chips on top of the package to the board on the bottom, you have to route electrical signals straight through the glass, using what are called through-glass vias, or TGVs. But with older conformal or full via plating methods, it's kind of like pouring liquid concrete into a really deep, narrow hole. It takes hours to dry, it's highly inefficient, and it almost always leaves these hollow voids inside the metal. And even worse, copper actually expands way faster than glass when it gets hot. So if that plated copper expands inside a fragile glass hole, the severe thermal stress will literally crack the glass right open.
So how do we fix that? Enter Part 3, KOSTECSYS' micro-pillar solution. To solve this brutal plating problem at the microscopic level, a company called KOSTECSYS developed this incredibly elegant engineering breakthrough. It's a brilliant four-step workaround. First, they form the tiny via hole in the glass. Second, and this is key, they manufacture a perfect, solid I-type micro-copper pillar entirely separately. Third, they drop this pre-made copper steel beam directly into the via. And finally, they vacuum fill the tiny little gap around the pillar with a highly specialized stress relief layer.
The real magic trick here relies on a concept they call block bonding. Basically, they are bypassing that incredibly slow, highly risky plating process entirely.
Instead of chemically trying to grow copper inside a glass hole and just crossing their fingers that there are no voids, they precisely insert high-quality, pre-made, perfectly flat copper pillars directly into the glass vias en masse.
Let's dive a bit deeper into why this works so well in Part 4, Advantages of Inserted Pillars.
When you look at how this comes together, the physical advantage is absolutely undeniable. You've got this perfectly straight, completely solid copper pillar. And these are unbelievably tiny, by the way, just 0.05 to 0.20 millimeters in diameter. But the genius part is the cross-section. That little blue layer surrounding the copper is a vital polymer layer made of materials like ABF, epoxy, or polyamide. When the solid copper inevitably heats up and expands, that soft polymer layer acts as a thermal shock absorber. It takes the absolute brunt of the expansion and completely saves the fragile glass from cracking.
And because they are popping in a solid pre-made piece of oxygen-free copper, you end up with a completely void-free structure, zero hollow spots. That means you get immense thermal conductivity. We're talking over 380 watts per meter Kelvin, which is exactly what you want for cooling down intense AI chips. Plus, thanks to that polymer shock absorber, it virtually eliminates glass cracking. Oh, and it offers a massive productivity boost because it completely skips the slow, bottlenecked plating process. It's pretty much tailor-made for those large area square glass panels we talked about earlier.
All of which naturally leads us to Part 5, the future AI supply chain.
When you combine TSMC's massive macro-level glass panels with KOSTECSYS microscopic pillar perfection, you're looking at a complete rewiring of the semiconductor supply chain as we know it. Reports indicate TSMC is aiming for pilot production of these glass panels by 2027, with mass production scaling up by 2028. And Intel is right there with them, pushing their own advanced tech. As this happens, all that high-margin advanced packaging is going to move completely in-house to these giant foundries. The companies that provide precision glass, advanced ABF films, and microscopic copper components, they are going to dominate this new ecosystem. Meanwhile, traditional organic PCB makers who just can't handle extreme microscopic precision are going to face a very tough road ahead.
So, that leaves us with a massive, open question to chew on. As standard packaging literally changes its core shape and material to keep up with the demands of AI, who's actually going to control the next standard of the global semiconductor supply chain? Will it be the traditional chip designers, the massive foundries adopting these new square panels, or maybe the highly specialized engineering firms mastering microscopic glass vias? You definitely want to keep an eye on this space, because the very foundation of artificial intelligence is currently being rebuilt on glass. Thanks so much for joining me on this explainer, and we will see you on the next one.